Good evening, class. This is class 3rd of assignment 3rd in class 4. Of electronic theory of solids. In this class, I will be covering majorly the part of the Hall effect, which is classical. Then a few problems from the quantum mechanics. And then I will end the class with Bloch theorem. Yeah. So having said that, I'll start the class right away, and just a minute. Yeah. So last time we had it till the Fermi energy and the Fermi temperature. All those things we covered up to the assignment 2. And now in this part, we'll be covering Hall effect, the quantum mechanics problems, maybe 1, 2 or 3. And then finally the Bloch theorem, that is the electron in a periodic lattice and how the wave function evolves in those cases. So having said that, let me start with the Hall effect. Hall effect is nothing but if you have, let's say, a semiconductor bar in which you apply a potential with the battery B, then, and this is your point A, this is your point B, and similarly you can have point C and D also. So when magnetic field, let's say a penetrating magnetic field B is there, which is perpendicular to this your bar. So in that case, for B equal to 0, VA will be equals to VD, right? If the bar is homogeneous, generally like homogeneous, then in that case potential at A will be potential at D, same. And similarly, VB is equals to VC, right? But when magnetic field is non-zero, what you get is VA is no longer equals to VD, and VB is also no longer equals to VC. And this is the clear signature that the whatever element which is carrying the current in the system is a charge particle, because when a charged particles, let's say an electron, moves in let's say the x direction, let me define, and this is Vx and this is y coordinate. Let's say it moves in the x direction with velocity v, then the force on it will be F equals to q, which is the charge, times E cross B, QV cross B, sorry, V cross B. Okay. So in this scenario, when your positive potential is applied here, negative here, so electron will move in this direction, right? From negative to positive. So your V is essentially minus Vx cap. Let's say your B is perpendicular Bz cap, and your charge is electronic charge minus E. Then the force will be minus E. V is minus V, and B and X cap cross Z cap. This is nothing but EVB, and X cap cross Z cap will be minus Y cap. So in that case, electrons will drift toward this end. If they accumulate on this edge, AB edge, then the potential on AB side will be different from the potential on the CD edge, and that's where the transverse voltage comes in. This is well discussed in the class already. And the important point to note is there that even if the charge particle charges change basically, let's say now if a hole is there instead of electron, a hole is there with charge plus E instead of minus E. Now the charge is plus E. Then your V will be actually Vx cap, because now they will move in the direction of the battery, right? The direction of the electric field, not opposite. So this is how they will move the whole carriers. So V will be Vx, B is Bz cap, and Q is E. Again, the force turns out to be EVB minus Y cap, saying that okay, irrespective of the charge, all the charges will move in one direction only, and that's a good thing, because if now the electron is there and on the bottom is B, the negative charge will accumulate, and if hole is there, the positive charge will accumulate, and by reading the voltage VTB, that is between difference between T and B, one can tell that whether, so VTB sign tells if carriers are electron or hole. And this is what's like very conventionally used in the semiconductor case to determine the different types of the carriers. Yeah. So this is about the basic introduction. Now moving on to the solving the problem. Okay. So now the question is, now if you are doing a whole experiment in a whole effect experiment, in a metal, a potential of, that is the battery micro, okay, this is the potential between A and B, the top and the bottom edge is developed. This is very small voltage. If you see, it's only microvolt, but that's enough to tell us what is the number of the carriers there in the system, what is their charge, all those things it can tell. Foil of thickness 0.02 mm. Now it says that when a current (1.5 ampere) is passed in direction perpendicular to the magnetic field, of 2 Tesla. 2 Tesla is a large magnetic field. So generally 2 Tesla of magnetic field is achieved using superconducting coil magnets, not the conventional, because it requires large like amount of the current, and that current generally warms up the wires and they get burnt. So generally to attain the magnetic field above 1 Tesla, people use superconducting magnets where the heat loss is not there. So the Hall coefficient for metal is, so this is what the question is. So you have you are doing a Hall effect experiment, of course with a metal. You can do it with a semiconductor also, but not insulator. Now a potential of 4.5 microvolt is observed. So this is Vxy. right, transverse to the current direction, and the thickness of the foil is also given, current passing through the foil is also given, and magnetic field is also given. All we have to do is determine the Hall coefficient. Hall coefficient, if you follow the class notes, is RH, denoted by RH, and nothing but EY by JXB. EY is the electric field in the Y direction, Jx is the current density in the X direction, B is the magnetic field. So you're having a geometry like this. Yeah, I think this is the geometry in which this thickness, this they have given to be 0.02 mm, extremely thin. I mean, so 0.02 mm is roughly 20 micron, and width also is there. Let's say it's W, and the transverse voltage which has been developed between X, Y is nothing but 4.5 microvolt. This is all what you have. Now, if I ask you, how do you write the EY? Because here we need EY, JX, and B. Okay, let me write EY. EY is the electric field in the transverse direction. Electric field in transverse direction. JX is current density. B is magnetic field. Current density in X direction. B is the perpendicular magnetic field. Yeah. So if I ask you how to write EY, you will say that okay, EY is nothing but VXY by whatever the width is there, right? And similarly, I can ask you Jx also, how do you write the current density? Current density you write total current divided by the area, right? So W, which is the width, and T is the thickness. That will give you the area, right? And B is the magnetic field. Now you substitute these values. This is equation 1. Both of these are equation 2. Substituting 2 in 1. So RH is nothing but EY is VXY by W times W times T by I is B. W goes away, but we are left with is RH is equals to VXY, that is the transverse voltage, microvolt, which whatever the value is given. T is the thickness, I is the current, and B is the magnetic field. Let's just substitute all the value. Vxy given value is 4.5 microvolt. So 4.5 into 10 power minus 6. Thickness is 0.02 mm. So mm we convert into the meter by multiplying 10 power minus 3. Current is 1.5 ampere and magnetic field is 2 Tesla. And if you do the calculation, what will you get is roughly around 0.3 into 10 power minus 10 meter cube per coulomb. So this is the Hall coefficient in the case of the metal, which develops 4.5 microvolt in the transverse voltage in a magnetic field of 2 Tesla, and the current when you are passing is around 1.5 ampere. Thickness is of 20 micrometer. So this is how you calculate the Hall coefficient. And what do you get if you know the Hall coefficient? You can determine the carrier concentration. Let's say, for example, in the same problem, is the next question related to this only. So, in the same problem, determine the electron density. So the relation between the RH and N is 1 by NE. So now you know the RH. So N will be nothing but 1 by RH times E. So RH is 0.3 into 10 power minus 10 into 1.6, 10 power minus 19. 19 and 10 will be 29, and it roughly turns out to be 0.2 into 29. It will be roughly around 2.08 into 10 power 28 per meter cube. So the important point to note is that this value of the RH, if you are measuring semiconductor sample, let's say like a bilayer graphene or like doped silicon or all those one, in that one the carrier concentration is very low. So your signal of RH is very large, RXY, transverse voltage. But in case of the pure metal, right, its value is very small and it's hard to detect. That's why these uh, this carrier concentration determination, all those things are very effectively done for the semiconductor using this technique of Hall effect. Is there any question on this one? Like I have completed these two questions on the Hall effect, which covers why the transfer voltage is there initially. Then in the next part, it covers the numerical part, that if a magnetic field is given, transverse voltage is given, and then thickness of the plate is given, then how to determine the Hall coefficient RH. Then in the next question, I discussed how to determine the carrier concentration, free carrier concentration. Of course, the carriers can be more than this one, but what the carrier, it means the number of the carriers, the average number of the carriers which are contributing to the electrical current. So these are 2.08 into 10 power 28 per meter cube, what we call the free electrons. Is there any doubt in this one or any question? You can ask in the comment section. So let me give you another idea on this one. How do I use this technique in my research of the PhD? So the system which I work on is a graphene system, bilayer graphene. So how do we use Hall effect? How do I use Hall effect? So the band structure, first thing you should look at the band structure. So the band structure of the bilayer graphene is like this, roughly parabolic. This is very rough structure I'm drawing. Right? So this is bilayer graphene. But if you make, okay, now if you take the RXY signal for this one, right, and so the RXY signal, if you measure here, this is your RXY, so it will be 1 by NE. So it goes like, yeah, so your RXY signal comes like this, and it shoots up, then it goes down. Yeah, that's how the RXY signal goes like. Right? At these carrier concentration, RXY shoots up because RXY is nothing but minus B by NE. This is at a finite magnetic field, of course, right? So on this side, your electrons are negatively charged. So RXY signal is positive. On the other end, it's negative. It's just a matter of how you define it with the magnetic field direction also. But this is how the RXY you will get. And for this reason, you will call that, okay, since RXY is positive, I'll call it like electron-like carriers. And in this regime, your RXY values are, okay, this is 0, are negative. So this regime you call hole-like. And that's what we know, right? If a band curves like this, it is hole-like band. And if a band has a curve like this, it is a electron band. That's what in the case of the bilagraphene, piston bilagraphene. And then if you plot like Rxy versus 1 by n, you will get linear line, and from there you can estimate the magnetic field and the capacitance values also. The things gets interesting which I work on is bilagraphene aligned with HBN. So you have a like bilagraphene initially. When you align it with HBN, the band gets like this. Yeah. So now if I draw this one, right, what will I get? Through the RXY, in the RXY signal, initially is the same, near charge neutrality point, nothing will change. But then, if you go on this side, whole side, a transition will come where, okay, this band is hole-like. Yeah, this band is hole-like, but this part of the band is electron-like, right? So we'll get a positive signal. Then there will be a sign change in between, and then there will again be negative signal. So it will be something like this. Yeah, and the same thing goes on this side also. Yeah, something like this. And from there we determine whether what kind of pockets are there, whether they're electron-like pocket, hole-like pocket, and all those fine details you can extract from this Rxy versus carrier density signal. Or let me write the energy. This axis is energy and this axis is K. So this is about how do we use Hall effect in our case. Now moving on to the next set of the problems, which is based on the quantum mechanics. Is there any question on this Hall effect? If no, then I will take the questions from the basically the quantum mechanics part. Okay then. So in the quantum mechanics, there are wave functions which determines like if, those wave functions. When an operator operates on those wave function and extracts the expectation value, that's the average value of the kind of the thing which you measure in your system. So that's the quantum mechanical concept. And whenever you measure a quantity, that state collapse basically into that one, whatever you have measured. So that also matters. So this is like the quantum mechanics, that how the physics is governed at the atomic scale and around those orders. That is very well explained using the quantum mechanics. So having said that, I'll start with the question, and then you will get a better idea. So consider a state of the wave function psi, which is again composed of orthogonal wave vectors of the phi i's, phi 1 plus 1 by root 5, phi 2, plus 1 by root 10 by 3. Okay, 5 i's of an are 3 orthonormal states where I goes to 1 to 3, 3 orthonormal state. So what is orthonormal? So if you have like phi 1, phi I, then it will be 1, or phi j for I is equals to j, it will be 1. For phi j is equals to 0, for I not equals to 0. That's what it means. Additionally, apart from that, how this state operates on the Hamiltonian and what the expectation value comes out from it is also given. So if an energy Hamiltonian H operates on phi I, you will get I square phi I. So this is about how the uh, basically Hamiltonian H operates on the psi i's and gives the output. Now comes the most critical part, which is now determine the expectation value of H. Okay. So now to determine the expectation value of a wave of a operator, what you should do is, let's say expectation value of H is essentially psi H psi divided by normalized psi i's. Yeah. So this notation is known as bra. This is known as cat, and this H is nothing but Hamiltonian operator. So if this is your H, so let's operate H on the wave function psi. So if it operates on the wave function psi, it will be H operating on 1 by root 2 psi 1 phi 1 plus 1 by root 5 phi 2 plus 1 by root 10 phi 3. Right. So this, the point to note is here is these phi i's, because whenever H operates on phi I, it gives I square. So let's see what we get in this case is H psi, okay, 1 square by square root 2 times phi 1 plus 4 by square root of 5 phi 2 plus 9 by root 10 phi 3. Now let's just take it Brian cut to this. So you get 1 by 2 plus 16 by 5 and I'm sorry, it's a mistake. Yeah, so it should be 1 by root 2 phi 1 plus 1 by root 5 phi 2 plus 1 by root 10 of phi 3 which is operating on now 1 by root 2 phi 1 plus 4 by root 5 phi 2 plus 9 by root 10 phi 3. So you do it, solve it, and what you get is 1 by 2 plus 1 plus 4 by 5 plus 9 by 10, right? And this gives us like 5 plus 8 plus 9 by 10. It's around 22 by 10 psi h psi. Expect. So this is if Hamiltonian operates on the wave function psi. But now we'll have to check the normalization factor also, right? This is the only the top part which we calculated here. So if you see in this part, this is what we calculated. Now we'll have to calculate the bottom part also to calculate the full expectation value. So that part is called normalization. Normalization of wave function. Yeah. So I have to take the normalization. I will do psi is equals to, it should be 1 ideally, right? If it's not normalized, if it's not normalized, then it won't be 1. Let's see. So that will be phi 1 by square root of 2 plus phi 2 by square root of 5 plus phi 3 by square root of 10 times phi 1 by square root of 2 plus phi 2 by square root of 5 plus phi 3 by square root of 10. Psi is nothing but 1 by 2 plus 1 by 5 plus 1 by 10. 8 by 10. So this is our equation 1, this is our equation 2, and this is our equation 3. Substituting 2 and 3 in 1. So expectation value of h, what we get is expectation value of psi h psi divided by psi, and that will be 22 by 10 divided by 8 by 10. So the value which you get is roughly around 22 by 8, even 11 by 4. So this is how you calculate the expectation value of any like what you call the operator. If you have any operator of which you want to calculate the Hamilton this expectation value, what you do is like you operate it like this. You first extract this part which is psi h psi, right? Where the Hamiltonian operates on the state cat, and then you um, calculate the expectation value by multiplying it with the operating with the bra, and then comes the second part, which is the normalization check. This is very important, very crucial normalization factor. If you miss the normalization factor, your answer would have been 22 by 10. But if you pay careful attention to the normalization, your answer is 11 by 4. There's a lot of a difference between these two. Yeah. Is there any question on this one? I would suggest I'm stopping here for 5 minutes. You go and do the revision of whatever the 3 questions we did. And if you have any question, uh, Q&A for 5 minutes. Just type in the text box. In the chat box. I will be answering those questions, because that is important to keep the things on the track, so that you guys understand whatever I'm saying, and also pay like careful attention to the key parameters being in the Hall effect, or in the quantum mechanics, how you extract the expectation values. Yeah. Yeah. Okay, if you guys don't have any question, yeah. So if you guys don't have any question, then I will continue the lecture, which will be there on this one more question from the quantum mechanics, and then 2 more questions from the block theorem. Yeah. So the next question which we have is like, if let's say your particle is confined in a 1D box, right, and now you double down the basically the length of your box, then how the energy scale changes in those scenarios. So that's something which I'll be uh, treating in this next problem. So let me just, yeah. The question is, con- consider two electrons in a box of length L. In ground state, given by epsilon naught. Now, two boxes are pushed together to form a bigger box. Then determine first the ground state energy, decrease in the momentum, and the first excited state. Okay, so what you have is like, let's say initially you had a box like this in which this is of length L, right? Now you had two boxes like this. This is another box, same. Now these two boxes are both together. So this one on the right, this one on the left, such that they merge and make something like this, which is around 0 to 12. And then in that also the ground state will be there. So the model is first asking what is the ground state energy, then it is asking what is the first excited state energy, and then in the last it is asking like what is the decrease in the momentum because of this merging. So we know that energy, ground state energy for party in a 1D box is bar square pi square by 2 ml square, where m is the mass of the particle. So this is the ground state energy which was there initially of length L. Now first L changes by 2L, then your energy, new ground state energy, will be E naught new will be h bar square pi square by 2m. Instead of L it will be 2L to the whole square. So E epsilon naught new is actually 1 by 4 times E naught over 1 by 4 times h bar square pi square by 2m L square. So this will be the new ground state energy. Now comes the first excited state energy. That will be n square pi square h bar square by 2m. Instead of L it will be 12 square, and for excited state n equals to 2. Here also n is equals to 2, so that will be pi square h bar square by 2 ml square. This is nothing but whatever the parameter given in the question, the ground state energy of like 1D box, that is E naught pi square h bar square by 2 ml square. Okay, so first excited state is equals to the ground state energy of the 1D box without merging. Now comes the final question, which is using uncertainty principle, Heisenberg uncertainty principle, prove that how the momentum changes in this case. So we know that delta x, delta px has to be greater than equals to h bar by 2. Or let's say for your simplicity, let's take it to be h bar just only. Right? So your delta x is nothing but your length, which is changed, and delta px is delta pxi, that will be h bar. Now this was the initial. Now in the final, L will be 12 times delta pxi, pxi final is equals to h bar. This is final. So this tells you that px final is px initial by 2. Yeah. So and this is about how the momentum changes. So if you have two 1D boxes and you merge them together, what will happen? Their momentum, uh, through the uncertainty principle, you can see that their momentum will come down by 2 times. And since energy goes as p square in general, so if your p is going by 1 by 2, your energy will go by 1 by 4. That's what you are seeing here. This 1 by 4 factor. This 1 by 4 factor. Again is the first excited state. So first excited state energy is equals to the ground state energy of the earlier one. Earlier in the sense without merging. Yeah. Is this clear to you? Like whatever we are doing and this calculation on the 1D box, how we determine the energy and using the uncertainty principles to find the final and the initial relation between the final and the initial momentum expression. If any question or doubt is there, please ask in the comment section. Don't hesitate. Otherwise, you guys will lose in the concept, and then again, then it would be a bigger problem. So whenever you have a doubt, even if it's a silly doubt, that's what it. Maybe you think that it's a silly doubt. Even also, then you ask the question, because if you ask the question, it will not only solve your doubt. Maybe some other your friend would also be having the same similar doubt, but they are hesitant to ask. So I always insist that to the students that please keep asking the questions. Yeah. So if no question is there, then okay, I'll move on to the block theorem part, which is essentially uh, the basically a theorem which governs how the which tells that how the electron moves in a periodic lattice. So I'll just start with the problem. So when we impose a boundary condition on an electron confined in a quantum well, only discrete values of k are permitted, right? Only discrete when we impose periodic when we impose periodic boundary condition on a string of n atoms. How many discrete values of k? are there, and what is their spacing. Yeah. So I think it's like, think it like a chain basically of 0 to length L, and now divide it in equal parts such that you can write, if the spacing between these two is A, you can write L is equals to Na, and this N is a very large number, right? Then, and Bloch theorem says that wave function psi x is nothing but ux e to the power iota kx, where u is the periodic function and e to the power I kx is the uh, plane wave basically. So, and yes, wave function, if you model it like a circle, once again, yeah, it's the same thing. If you model it like a circle, such that at the boundary condition, the 0 and L points are identical. In that case, here psi 0 will be u0 e to the power iota k0, and the psi L will be ul e to the power iota kl, right? And here psi x at x is equals to 0 will be same as the psi x at x is equals to L, and we know that u0 periodic boundary condition also will be equals to ul. So this if you combine these ones, what you get is e to the power iota kl is equals to 1. That's only possible when kl is equals to some integer 2 times some integer times the pi, where n belongs to integer. So k is 2n pi by l. So this addresses the question, which is like how many discrete values of k are there. So now we know that there will be 2n pi by l number of uh, discrete values will be there, and you can write it like as L is basically NA. So 2n pi, okay, here also I use capital N, then I should use M here, otherwise there's a mismatch in the symbol. So then I should use M here, 2m, and then M belongs to integer, yeah, 2m pi by NA. Yeah. Now, the next question which it asks is about the separation between these two. So separation delta k will be, this is km, right? So km plus 1 minus km, that will be delta k. Delta k will be 2m plus 1 pi by na minus 2m pi by na. So that's not, this gives you 2 pi by na delta k. So that's the spacing between the adjacent sides basically, 2 pi by na. Yeah, so uh, this is it. With this one I'll conclude the class. So now I'm open for questions. I'll be waiting here for next 5 minutes. If anyone has the question or doubt, they can ask in the chat section. Please ask in the chat section. Additionally, apart from this, next Saturday I won't be having class because I'll be traveling for some good reason. So maybe I'll take class on the Monday or Tuesday, which I'll inform through the mail. So you guys will get the mail, and then accordingly the class will be rescheduled. Apologies are there for the inconvenience in the schedule, but it's a hard deadline, so I'll have to meet that one, and I can't take class on the coming Saturday. Yeah, so the question which you submitted, if it has been graded, yeah, you can ask it. If the grade time is still pending, then I would say you refrain it from asking the question. But yeah, yeah, similar question you can ask, and then we can have discussion on that. Yeah, if it has been evaluated, then you can ask the question. Okay, I don't see any question or comments now coming from any of you guys. Then, if there is no question or anything to ask, then I'll take your leave. I'll see you maybe on the Monday or Tuesday. Thank you for being in the session.